Okay, so let's start our fourth session. We finished chapter 5 and we move on to chapter 6. It's at this page one uh 133 133. Okay, 13. I mean, a lot of ways to pronounce it, but 133. Okay, that's American English. Okay, yeah. 133 page. Okay. This is the best linear unbiased estimator. So we want to do the best. Best has a lot of meanings. Linear meaning linearity. Linearity meaning that it's a function. It's a linear function of the data, and it's unbiased. Then of course, you all know about unbiasedness. Unbiasedness means that if we take the expectation, it has to be equal to the true value. And best. So let's see uh, how we how people look at what's the perspective in which people look at this. Okay, it it's very frequent that in practice, an MVU estimator cannot be found. The problem is that so, a lot of times the parameter or the functional form of the signal model is very complicated. It's nonlinear function. So if you want to find the estimator, it's very difficult. So we may be willing to assume a model for it to make it simple. The point is we want to make it a little bit easier, make it a little bit easier. Okay. So in some sense, we will say that in previous chapters, it's in a more ideal situations where we have factorization or we can find things that when taken expectation equal to the true value. So, but in a lot of times we cannot do that. We are unable to do that. So in this case, we'll just sort of compromise a little bit. We compromise, we sacrifice a little bit of the nice properties, and then find things that are simpler and easier for us. Okay, this is meaningful in many engineering scenarios. So a common approach. Let's look at this. A common approach is to restrict the estimator to be linear in data and find a linear estimator that is unbiased and minimum variance. So we will turn the best unbiased estimator. So the point is, you see the point. The point is linear. Linear and what? And minimum variance. Okay. So in this concept of best, we're talking about variance. Okay. All right. So let's take a more detailed look at this. We observe the data set x0, x1 all the way to xm minus 1. And the PDF depends on an unknown parameter theta. The BRUE restricts the estimator to be linear in the data. So it will be theta hat equal to summation of A xn. Okay, so this is the definition of linearity. You multiply coefficients with the data and do the summation. This is the only thing you can do for linearity. If you do more than this, you're going out of linearity. Okay. For example, if you take the square, of the data, it's not linear. It's not linear. If you multiply the first data with the second data, it's non-linear. If you take the trigonometric function of the data, it's non-linear. Okay, all those things are non-linear. The only thing you can do is you multiply it with the coefficient and then take the summation. That will be the definition of linearity. Okay, so again, 我们又要讲那个老故事了。那个老故事就是那个 DC level 在 WGN 的那个最典型的 model。In this model, the theta hat is equal to sample mean, and then it's equal to 1 over n divided, 1 over n multiplied by xn. Does it fit the linearity model? Of course it is, right? It is. This is a typical linear model. This is a typical linear model. Then we are happy. We are happy because we have an estimator that is linear minimum variance. So this is a blue. This is a PLUE for the DC level. Okay, so this is a good example. Then let's take another example. If we restrict our attention to only linear estimators, then we will lose nothing because the NTHU is within this class. Okay. On the other hand, for the problem of estimating the mean of uniformly distributed noise, the NTHU was found to be there will be an example for this, but for now, let's just skip the details and the outcome. If you have a uniformly distributed noise and you want to estimate the mean, the NTHU will be this formula: theta equal to n plus 1 divided by 2n max xn. The point is, this is nonlinear. Right? This is nonlinear. You have a bunch of data, x, for example, x1, x0, x1, x2, all the way to x minus 1. And then you take the maximum. Will that be linear? Of course not. That's not linear. Okay, so if we restrict our estimator to be linear, then the PLUE is the sample mean. But the point is what? The point is we have a minimum variance estimated this to be this, but the PLUE in the linear domain, the best one is the sample mean, which is not equal to this, right? It's not equal. Then the PLUE for the point is the PLUE for this is suboptimal. It's no longer optimal. So as you know, we have demonstrated two examples. One is this one, that is DC level in WGN. The other one is the DC level in uniform noise. And you see different arguments. The first one is we have PLUE and NTHU to be the same thing. But for the second one, you have NTHU to be this, but sample mean as the PLUE. They are not equal. Okay, so we have to be careful that in a lot of scenarios, the PLUE is a rather restrict domain. The linearity, so to speak, the linearity is the limitation as a result, you may not be able to come up with the best estimator because the best estimator is nonlinear. Okay, I think I'm giving you a brief overview of the linearity, the PLUE, the linearity domain. And I think it's about time and we take a break. And that's all for today. That's for this today's class, and we'll continue next class. Okay.